Hello and welcome to the second lesson on time series analysis in R. So in this lesson we'll cover exponential smoothing, and we'll cover three methods. Simple exponential smoothing, the Holt method, and the Holt-Winters method. So to begin, load the precipitation data set into R. So I've called that rain. If you bring that up, that gives you the precipitation in millimeters in a U.S. city from 1940 to the end of 1950 for each month. So to start, let's convert our data into a time series object. So I'll copy and paste the command. And what I'm doing is taking that second column of my data frame, putting the frequency to 12 because there's 12, it's monthly data, so there's 12 months per year, and then just indicating the first time point is January 1940. We plot our time series. We have a time series plot of the monthly precipitation levels. Now, to fit a simple exponential smoothing model, we're going to use the Holt-Winters command. So let's call our model SES forecasts and give it the value Holt-Winters. Now we input our time series. Now a simple exponential smoothing, remember there's no beta or gamma, so we're going to set those parameters equal to false because we just want to fit a simple exponential smoothing model. Gamma is false, and we can set the initial value to be the first point of our time series. This might be the default for this function, but just to be sure we'll input it and run that to fit the model. And now let's print that and take a look at our parameter. So here you can see our alpha of 0.148. So remember, the alpha is the weight on recent values. So there's relatively low weight on the most recent values for this particular fitted model. Now we want to extract our forecasted values from our simple exponential model that we just fit. So we can do that by typing SES forecasts, select fitted, right? So this SES forecast, this model, has some components once you fit it, and the forecasts are stored in a component called fitted. So hit enter, and you can see it prints your forecasts starting in February 1940 down to December of 1950. Now there's two columns here. They're repeated in this case. That would be different for the later models that we'll do. So what we really want though is we don't want these columns repeated. We just want to extract the one column so that we have a time series for our forecasted values. So to do that, let's just create an object called forecast values, and then we'll write the same command we just did, SES forecasts select fitted, but we'll just take that first column because we just want a simple time series of our forecasts. So if you look up here, our forecast values is now a time series object, and you have 131 entries. So if you wanted to calculate the mean square error for your time series, let's first define the squared errors. So remember, that's just going to be the difference between your time series values minus your forecast values squared. So that's basically your sum of squared errors. And now the mean square error, or pardon me, not your sum of squared errors, those are your squared errors, right? You have 131 of them. And then your mean square error is the sum of your squared errors divided by the number of values. So that's going to be sum errors divided by 131, right? That's how many forecasts we have. So you get an MSE of 1,552.214. Now you could calculate that another way. If you were to type SES forecasts, now remember before we extracted fitted, but there's also a sum of squared errors component stored in there. So if you were to divide that by 131, you should get the same value, right? Because the mean square error is simply the sum of squared errors divided by the number of values. So hit enter, and as a check, we get the same value. So we can plot our forecasts. We type plot SES forecasts. So you can see the original data in black here, and your fitted simple exponential smoothing model shown in red. If you wanted to just plot your forecast values alone, you could do that with the command plot forecast values, and that would just give you the curve that was in red on the previous graph. Now remember, the idea with time series is that we want to forecast into the next period or periods. So we can do that with a package called forecast. So if you haven't done so, install that package and then load it with this library function, or sorry, the library command and input forecast. And I believe it's already loaded on my computer, but if it's not on yours, you'll see R loading that. Now we can use that forecast package to predict what the precipitation will be starting in, say, 1951. So let's create a new object here. We'll call it SES forecasts new, and that'll get the value. Now we're going to use this new forecast function from the package we downloaded, and as input we have to use our already fitted simple exponential smoothing model, right? So SES forecasts, that's the model that we fit before. So we input that into this forecast function, and then input the number of periods that we want to forecast for. So suppose we wanted to know the monthly precipitation in 5 months. Well, we type h equals 5, run that, and then take a look at our new forecast. So here you get the a forecast from January to May in 1951. This particular model, they all happen to be the same value, but as you can see, the confidence bounds change. So here you have an 80% confidence interval and a 95. So obviously the 95 confidence bound will be wider than the 80, and you can see the further out we go, the wider the confidence bound is, right? The May confidence bounds are wider than the January confidence bounds. So if we wanted to plot that, we could type plot SES forecasts new, and that will give a plot of our forecasted values as well as the confidence bounds. We could also create a plot of our forecast errors. Sometimes it's a good idea to ensure that they're centered around 0, make sure they don't have any particular trend or odd components. So if we type plot SES forecasts new, and then select the residuals, which is our forecast errors, hit enter, and let's take a look. So you can see our forecast errors are centered roughly around the 0 line, so that looks good.